Okay. So, good evening, everyone. Welcome to week 10 of the Electronic Circuits course, my problems session. I'm Neksha Devi, a PNRS fellow. So, in today's session, we'll talk about multi-stage amplifiers. So, when we say multi-stage amplifiers, these are the amplifiers with more than one stage, and typically these have
Hello.
yes.
Your voice is a little low actually, like audio wise, it's a bit low.
My voice is a little low.
Yes. I mean, it feels like sometimes you're further away from the speaker, like that.
Okay. Hello.
Yes, ma'am, now it's clear.
Is it okay now?
Yes.
Okay. So since I'm in room, so I can continue like this. So yeah, when we talk about multi-stage amplifiers, we have basically two type of multi-stage amplifiers. One is cascade, another is cascode. So in cascade, what happens is we have one stage of amplifier. The output of first stage is given to the input of second stage. So these are multi-stage CS amplifiers where output of one stage is given to the input of another stage. This is the cascade configuration. Now when we talk about cascode, in this configuration, for same gain, I'm designing a cascode amplifier as well. Okay. So in these two configurations, both cascade and cascode, these are two-stage amplifiers. The gain will be same for both of them. So it's like gains are almost equal in both these configurations. So here what is happening is the output of one stage is given as input to the second stage. This is cascade. Whereas in cascode, rather than using two different stages, what we do is we stack transistors one over another. Okay. So here your input goes from one transistor. It goes through the uh, drain terminal of the transistor to the source of next transistor. From there it comes out through the drain as output. Okay. Now if we look at this carefully, if we note about few things, so first of all, as I mentioned, the gains are almost equal. So gain is like second order gain will be there for both the cascade as well as cascade configurations, so we don't have to consider that. Other than that, if I talk about, okay, how many number of poles are there in our system, so if we talk in the first cascade, here we will have one. So one is your AC node is here where you will providing the input. Then second node is here and third is at output. In the cascode case, you have one at input. This is your AC node, and then you have a AC node over here, and there is another AC node which will appear here as well, right? And so here also the transistor is like source, drain, source, drain. So this is how the transistors are arranged. If we talk about their advantages and disadvantages in terms of the factors, so it will be even clear to understand how these two configurations can be identified, right? So let's say here we have features. This is for cascade and this is for cascode. So starting with what are the features that we can talk about in a system, right? First of all, gain. Gain is something that we need to keep in mind. Other than that, the next thing that we have to understand and to be aware of is power dissipation, correct? So one is gain, another is power dissipation. What else do we need to consider? What else we have come across while these many sessions that we had till now? We are at 10th session, right? Till now we have been dealing with amplifiers. So what are the critical what are the critical aspects that we discuss about in an amplifier? So one is gain, one is power dissipation. What else we have observed in our systems?
Swing limits.
Yes, output swing, especially output swing. So we have output swing. What else?
Uh, Z in or Z out, R in, R out.
I mean, R in, R out is okay, right? Because we are giving input from gate and taking output from drain in both the cases. So I guess R in and R out will be almost comparable, right? So there won't be a problem. What else can we talk about?
CMRR.
CMRR. Okay, so CMRR comes into picture when you have a differential amplifier, and these are not differential, right? So, we need not to consider CMRR over here, considering that it is a single stage. Like, it's not differential, rather, it is only single input, single output kind of amplifiers. So, CMRR will not come into picture, but CMRR will definitely come into picture when you have a differential amplifier. Okay? Yeah, what else? What else have we come across till now? Anything else that comes to your mind? Okay, so there is something that I talked very briefly about, almost negligible. We'll discuss it in quite some detail in coming lectures, but one of the major constraints in any circuit uh, possible is stability of the circuit. Okay, so we will talk about all these features for corresponding to these two particular configurations. Okay. So starting with gain, I said they have almost equal, almost equal gain. So if I have to give you like the approximate values that will come out for both of them after certain assumptions is So the gain will be GM upon GM square upon GD square. This is the approximate gain which you can obtain in both the cases. By doing some approximations, you will get almost equal gain, right? Now, if we talk about power dissipation, so you see in cascade you have two different stages. Both the stages will draw some current, right? And VDD is same. So VD equal to ID1, power dissipation will be VDD into ID1 plus ID2 in case of cascade amplifier. Whereas when you see a cascade amplifier, it only has a single branch. So it will only draw one current, which is, let's say, corresponding to I1. So here the power dissipation will be VDD into I1, right? So if I write the power dissipation, it will be ID1 plus I2 or VDD into I1. So from here we understand that, okay, in cascade my power dissipation will be high, whereas in cascade the power dissipation would be low. This is one thing. Now, if we see output swing, so swing, we know that the total signals, whatever are there, will be confined between your VDD to ground, right? So, if we see in the single stage amplifiers, here there will be some drop, this particular drop of VDS or VSD across your PMOS. Then there would be some drop of VDS across NMOS. Then beyond this, you will have some swing of V out, right? So VDD to ground will be distributed as VSD plus VDS plus V out swing, correct? Output swing. This is how your total VDD to ground will be divided into different parts, right? In a single stage amplifier. Now see, when you have a cascade amplifier, the problem is here you have a drop of VDS because of this first transistor. Then you have another VDS or VSD, I should say, because these are PMOS transistors. So VSD. Then you have some V out swing. Then you have VDS of NMOS transistor, VDS of another NMOS transistor, right? So in this situation, if I write like VDD to ground distribution, I have VSD plus VSD plus V out swing, some swing, plus VDS plus VDS, right? So from here we can clearly observe that the advantage that we get because of our cascade amplifier is in terms of swing. So here the output swing that you will obtain is high compared to the cascade configuration, correct? Now, the most important part that we haven't discussed yet, however, we'll discuss it most probably next week. It is the stability of system. And when we talk about stability of the system, it again comes from the pole zero analysis. And majorly we talk about stability based on the phase margin. So we have seen Bode plot, right? We understood Bode plot, but majorly we talked about the magnitude Bode plot, right? Which was magnitude versus frequency plot. We did not talk much about the phase plot, where what is the how the behavior of phase changes with the introduction of a zero or a pole, correct? But when we talk about stability, at stability, so the major concern that we have is with respect to the phases. And when we say phase margin, it is basically we at a certain frequency we try to obtain the cumulative phase of the system, and depending on that particular phase, that is known as phase margin. So there is certain expression to find out the phase margin, and depending on the phase margin we comment whether the system is stable or not. Okay, so it comes from the placement of specially poles. So in our case, poles are very critical. So if we talk about the uh, bandwidth of the system, then also you look into the poles, right? Because poles will provide you the bandwidth. Similarly, when we talk about the stability, there also poles are something that are very critical to us. So in next session we will definitely talk about stability, but for now, to keep just this point in mind, that in this case, when we talk about stability, so if we see a cascade amplifier, so you know that first of all the pole which comes at the input, we know that it is at gate, so the frequency like 1 upon RC will be very small and neglected, so we don't consider that. Other than the input pole, we consider all other poles, right, in the system. So, if you see the cascade stage, here you have two poles, this and this, right? So, but these two poles, if you observe very carefully, these two are almost equal poles, because the impedance that is coming because of the gate of second stage is infinite. So in the calculations it will not come into picture. So anyhow, it turns out that the pole in A is very close to pole at B. The value of pole at A point is very close to the pole at B point. So it behaves as a two poles at same point kind of behavior. So we know the more the poles, the steeper our Bode plot will become, right? So similarly, the phase also changes accordingly. So that's why it basically leads to reducing the stability of the system. So the cascade stage has low stability, whereas compared to your cascade stage, it has higher stability. Okay. So if we have to analyze the cascade stage, we can analyze that. How? See, here, let's not talk about the capacitances for now. Considering that capacitances are almost comparable, let's talk about the impedances. So if you see at this particular stage, so here you have A, B, and C points, right? So if we talk about the resistance coming at A point, it will be a resistance coming from source parallel to the resistance from drain. So this parallel combination of RS and RD will give us a small resistance, correct? So 1 by RC will be a larger pole. So this pole will come in the further places, like at the higher frequencies, correct? Now, when we talk about the pole that is coming at B, so at B, you see you have two drains connected. So it will be RD parallel RD. So this particular will be RD by 2, right? The resistance will come out to be, considering that RDs are comparable or almost equal. The resistance will be almost equal to RD by 2. Whereas when it was RS parallel RD, we know in parallel combination, the resistance, the equivalent resistance comes out to be lesser than the smaller value. That is always true. So that means the resistance at A point, so ZA, would be less than RS, whereas at ZB it is almost equal to, let's say, RD by 2. Similarly, ZC should also be less than RS. So because of these, what happens is the poles that will be coming because of A point and C point, they will come at very higher frequencies, whereas only one pole will be there which will be coming because of the point B, which is the Z out point, and this is the only point that will be the dominant pole. So what is the dominant pole? So the first pole, generally the first pole that appears in your system, we call it as the dominant pole, because what we consider is until any pole has appeared, you say that your transfer function is almost stable, right? It is almost constant, and you define your bandwidth also in terms of your dominant pole. So it is very important to have a dominant pole, and these dominant poles basically define the stability of system as well. So in this particular cascode system, you only have single pole, and which is a dominant pole. So because of which it will provide you the advantage with phase margin. We will discuss this in much greater details in the next session. But for now, keep in mind that the cascade is the cascade amplifier, multi-stage amplifier, has lower stability compared to cascode amplifier, which has higher stability. So but we do use cascade because it gives us advantage with the output swing, right? So how to increase or improve the stability? To improve the stability, what we do is a compensation capacitor is applied. Okay, a compensation capacitor is applied at this particular point. We call it CC. Its value is such that it will separate these two poles which are coming between A and B. They will be farther apart, such that you will get a system which is equivalent to a single dominant pole system. Because the idea is a single dominant pole system brings stability to the circuit. So we always try to design a circuit with a single dominant pole. That is the idea, to retain the stability of the system. Okay, so these are the things you can keep in mind, and with this, we can go ahead and solve our problems.
Excuse me, ma'am.
Yes.
Can you repeat the part of output swing?
Output swing. Okay. So see, output swing. What is output swing? Is basically at output you will get some sine wave, and that sine wave should come out to be a complete sine wave. There should not be any. Uh, what should I say? There should not be any um, clipping or those sort of things in your signal, right? So you know that your devices will draw some voltage, right, for operation. So you know that when there is a MOSFET, in this particular case, like if we say this in cascade stage, this particular MOSFET, when you come from VDD to ground, in that case, it draws some voltage of VSD, that is source to drain voltage, that will drop across a MOSFET. That is always there. Similarly, the NMOS will also draw voltage of VDS. So, like if I draw, let's say my limit is VDD to ground, and here if I have to draw, okay, how it will look like. So I say, let's say my VSD comes out to be at this point, VDS comes out to be at this point. Okay, so this much voltage has already been used. So the remaining, this particular region will be used for output swing, correct? This is clear.
Yes, ma'am.
So now, the moment you start stacking your transistors, what will happen is one transistor was drawing a voltage of VDS. So the next transistor, since the transistors are almost matched, they will also draw the same voltage, right? considering the transistors are matched. So other transistor will also draw a voltage of VDS. So in this case, if I have to split my VDD to ground, how it will look like? So here I will have one VSD because of the transistor 1. Then the transistor 2 will again draw some VSD, say equal VSD right now. So this much. Now here you have VDS because of NMOS. Same VDS will be drawn because of second NMOS. Now see here, the output swing has been limited by this value, right? And which is much smaller compared to the cascade stage. So it is clearly visible, correct?
Yes, ma'am.
So that's why I said that cascade will, so cascade basically will provide us with the advantage of output swing, whereas it is a problem with cascade stage. Is this clear?
Yes, ma'am.
Yeah. Now, the thing is, you can have hybrid circuits as well. By hybrid, what do I mean? So it's like first stage you can prepare it with a cascade, and then you can make it like multi-stage of cascades or cascodes. So that means your first stage is a cascode circuit, then its output is connected to the input of another cascode circuit. So by that it is basically you are following like cascading in the stages, whereas cascode in the single stage. So like that hybrid this multi-staging can also be done. And also this can be used in multi-stage as well, because in multi-stage, see, sorry, multi-stage, I mean differential phases as well, because at the end when you talk about differential amplifiers, they are also like normal amplifiers, right? You do want gain out of them, you want very high gain differential amplifiers. So for increasing the gain in the differential amplifiers also, you can go by using cascade stages as well as cascading. So these two, and also hybrid is also hybrid of these two can also be used. So these are simply the concepts of cascade and cascode, but these can be implemented in the differential stages as well. Okay, so yeah, now with this basic information, let's dive into today's problems. So starting with the first problem. So in this problem, it is mentioned that you have a VDD of 12 volt, I reference is 2 milliamperes. Okay. So you see, it is a cascade current mirror. Why cascade? Because you have two stages, one back then other. And when you have your gate and drain connected, right, this kind of configuration, whenever you see this kind of configuration, remember something in mind, that this will provide you the mirror effect, or this is basically the mirror circuit. Okay, so the moment you see this gate to drain connection, it will simply, you can make sure that okay, the other stage that is connected would be either mirroring the current, or it will multiply the current depending on the transistor factors. So whenever you see this connection, you can think it from that perspective, like either it is replicating the current in the other branch, or it might be manipulating with the current uh, based on the transistor widths. Okay. But something that you can also observe over here is that in these, like if I talk about in the uh, single stage, here you have one NMOS stacked above another, right? So this is like drain of source of one transistor is connected to the drain of another transistor, right? So here source is connected to the drain, which is similar to this cascade behavior, right? This behavior. So you can simply see that that behavior is also being replicated over here. So yeah. So with this you can now think of, okay, so this is basically now looking at this particular circuit, you have two stages similar to the cascading. Then you can also see that it is PMOS stacked over NMOS stacked above NMOS, which is similar to what we see in the bottom half or lower half of the cascade configuration. And then also you have this uh, mirror, so mirror will be definitely used. Other than that, what else can be drawn from this particular circuit? What other information can we draw? So yeah, more or less this much information we can draw just by looking at the circuit without reading any problem or anything, right? So
Can you please explain like how is it a cascade? In what sense? I didn't
cascade
quite
is
follow.
just cascade. It is because it's just that like there are two stages which are connected one beside the other. That is the only reason that we say it is similar to cascade. And also like the current from one stage is moving to another, right? So
Uh,
that's why. So these two, if you see, like there is one part this and there is another this part, right? So these two parts are back to back connected. So when you see like back to back connections, we say it is cascade configuration. And when they are connected one above the another, we call it cascade configuration. So just because of that, this has been named as cascade. Okay, because you have two different stages. That's the only thing. And
uh,
yeah,
but do we have like the current moving from one stage to the another stage? I mean, because both of them are correct connected through the gates.
yeah, both of them are connected through the gate, but we have mirror configuration, right? So
Yes.
mirror basically makes sure that the other branch will get the current, and it will be always proportional to the parent branch. That is because of the mirror.
Mm,
So yeah, so
uh,
because of the mirror, we can say that this is cascade because this mirror circuit. So the parent branch with reference current will lead to the current in the second branch. So that's fine. Here it's
um,
not about the input voltage, rather it is with respect to the currents. So that is the only thing. That's why it is mentioned cascade mirror. Otherwise, if you can say you can, if you see like stacking of back-to-back gates, back-to-back transistors, one above the another, then from that sense we can also see, okay, this is somewhat resembling the cascade configuration as well, right? So yeah,
um, so there would be like a series of just like transistors put above another, and then
yeah.
uh,
So if they are put one above another, such that, so it's like if you have drain source type of connection where one drain is connected to the source of another, that means they are stacked one above another, right? So that is
yes.
cascade. And when you see that like they have multiple stages. Like one thing is, so there is one stage, then from that stage it is moving to some second stage. So basically the output, what will move? So it's the output that you transfer from one stage to another, right? So when that kind
Yes.
of situation is there, then it is cascade.
Okay.
Yeah.
Uh, Thank you.
Okay. So yeah, coming back to the problem now, we know that okay, this is a mirror circuit with some cascade kind of configuration. So the idea is to find the DC voltage V3 between the drain of M3 and ground, such that the DC current that is flowing through transistor M3 as well as M2 is 2 milliamperes. Enter the closest answer possible. Now here, since we have kW by L given as 1 milliamperes per volt square, VTH is 1 volt, lambda is given, so we can use lambda, and we know that the current flowing through the transistor M3, so let's say I write it as IM3 is equal to IM2 because these two are in series, and it can be written as kW by 2L VGS minus VTH whole square 1 plus lambda VDS, right? Now here if right, okay, so VDS3 is VDS2 plus no, so V3 is basically VDS3 plus VDS2, right, from the circuit, and this VDS2 is V2, correct? So if I write like IM2 as kW by 2L VGS minus VTH whole square 1 plus lambda VDS2, so this is basically kW by 2L VGS minus VTH square 1 plus lambda V2. So we know V2. This is equal to 2 milliamperes. This is something that we already know, right? Now here, what are the things that we know from here is here all four transistors are identical, okay? So whatever is happening with M1, M4, similar behavior will happen more or less with M2 and M3 as well. So if I talk about transistor M1, in M1, IM1, we know it is 2 milliamperes, right? Because there is a reference current that is flowing through this and which is of 2 milliamperes. This can be written as kW by 2L VGS minus VTH whole square 1 plus lambda VDS 1. Now here if we see, the VDS1 and VGS1 are both equal. So by that I can write yes. So from there, if I substitute like so, let's say in place of VGS1, I am substituting VDS1. So VDS1 minus VDH whole square 1 plus lambda VDS1. Or I can make it like vice versa. VGS, let's use VGS just because VGS1 and VGS4 are equal. So I cannot comment about VDS1, VDS4, but definitely I can comment about VGS1 and VGS4. So that's why let's substitute VGS over here. So this is 2 milliamperes equal to 1 milli by 2 into VGS1 minus 1 whole square 1 plus 0.01 0.01, right? Yeah, 0.01 into VGS1. So here you can see that this is a cubic equation of VGS1. So this is a function of VGS1 cube. So this will be a function of VGS1 cube. When we try and solve this, what we'll get is 4 times VGS1 square plus 1 plus 2 minus 2 VGS1 into 1 plus 0.01 VGS1. So the expression will be VGS1 square minus 2 VGS1 plus 1 plus 0.01 VGS1 cube plus 0.01 VGS1 minus 2 VGS4. So it is 0.02 VGS1 whole square. So this is the expression that we will get, and finally when we simplify, what we get is 0.01 VGS1 cube plus 0.98 VGS1 square minus 1.99 VGS1 minus 3. Okay. So this is the final expression that we will obtain, and since it is a cubic expression, we'll definitely get 3 values for VGS, right? VGS1. And the 3 values turn out to be minus 99.96, 2.97 and minus 1.01. Okay. So see, first of all, this is never possible because your gate voltage can never go beyond VDD. So that is negligible, like that is neglected. Then next you have VGS of 2.97 and VGS of minus 1.01. See, the transistors that you have here are NMOS transistors. NMOS transistor only turns on when you have a positive voltage. Positive gate voltage only can turn on your NMOS transistor, right? So your VG should always be greater than VTH. Because of that, it is clear that VGS1 would be 2.97. Right? Now, we also know because of this mirror circuit, we clearly know that VGS1 is equal to VGS2. So, this value will be used in this particular expression, this one. So, here we will use at M2, 2 milliamperes is kW by 2L, VGS2 minus VTH whole square 1 plus lambda VDS2, or I can directly write it as lambda V2. Correct? So here you have 2 milliamperes, 1 by 2, 2.97 minus 1 whole square 1 plus 0.01 V2. So here we can simply solve, and what we will find is V2 equal to 2.97 volts, because it is the same expression, right? So directly from there we know that V2 is 2.97. Similarly, when the similar expression is like similar way, when you solve for VGS4, it will come out to be VGS 3, and it will also come out to be 2.97. So basically VGS1 equal to VGS2 VGS1 equal to VGS2 equal to VGS3 and VGS4. All of these are 2.97 volts. And in the similar way, your VDS1, VDS2, VDS3, VDS4 will also come out to be 2.97 volts. So this V2 is VDS2. So from here we know that V3 equal to VDS2 plus VDS3. So that is 2.97 plus 2.97. So this is V3 of 5.94 volts. Is this clear? Okay. So if this is clear, let's move on to the next problem. So this was very simple. We didn't do anything. It's just we used the concepts of mirror as well as series transistors. So the current being constant. That's the only concept that has been used. Now from here, it is asked that find the small signal output resistance looking from M3, this resistance for the circuit. So if we talk about this particular resistance, now what are the resistances that you can observe over here? So the resistance can be given at that point is GM3 R03 into R02 plus R03 plus R02. So this is how the Z out will look like at M3. Okay. So this has been also discussed in the lectures, so you can go through that. So from here we know that okay, we have to find GMs and R0, then we can simply substitute in this equation. So first of all, if we talk about GM, we know it is 2ID into KW by L, correct? So from there we'll have Ys of 2 milli into 1 milli. So this will be 2 millisieverns of GM, and we'll have R0 can be given as 1 upon lambda I. So R0 is 1 upon 0.01 into 2 milli. So this is 50 kilo ohms. So from there the Z out turns out to be 2 millisiemens into 50k into 50k plus 50k into plus 50k. So here we will get so Z out will almost be close to 5 metohms. Right? So this is the Z out that will be observed.
So in case the application modules are not or R was also given, so that would be a parallel combination, right?
Yes, that will come into parallel if it was
Okay.
mentioned. Yes.
Okay, so if it is not mentioned, we'll just take off
Yeah,
the
yeah. So,
transistors.
if it, see the information, if it is not mentioned, then you can simply ignore it, considering that there is negligible amount of impact coming from that particular, like, whatever it is, that particular component. Because you cannot deal with it otherwise, no? Because there is
Yes.
no information given, so better to ignore it. So that's
Okay,
the,
got.
yeah.
Thank you.
So, moving on to the next problem. So, this is again using the same circuit. Now, here what we have to do is find the minimum DC value V3 with which the small signal resistance remains high. So, here we need to find the minimum V3 such that the small signal output resistance remains high. So the minimum, okay. See, when we talk about minimum VDS, right? It's with respect to saturation, especially in case of amplifiers. You want your amplifier, so the transistors in the amplifier to be in saturation. Now, when you are talking about minimum conditions, especially when it is in the case of your VDS, it is the minimum saturation VDS that is required. So, how do we find the VDS min? We know VDS min is VGS minus VTH, correct? So, this is the idea. So, basically, your VDS minimum comes from this saturation limit, that is VGS minus VTH. So here we are asked to find V3 min, correct? So what is V3 min? So V3 min, so first of all your V3 consists of VDS3 plus VDS2, and if I talk about the V3 min, so that means in case of your VD3, we know like V3 min, for min we can write VDS3 can be written as VGS3 minus VDH. This is the minimum possible VDS that can be applied across transistor 3 plus VDS2, because that is coming from the second transistor. So from there we can get like V3 min as 2.97 minus 1 plus 2.97 coming from our transistor M2. So because of that we will get V3 min, that is the minimum condition to be how much? This is 5.94 minus 1, so V3 min is 4.94.
So in this case, we haven't considered so this VDS2 we found out, right? But
Yes.
VDS2 can also have a minimum value which can be like VGS2 minus VTH.
Okay, so if we analyze it other way around, we can analyze it like, let's say for the transistor 2, okay? So the transistor 2 for N2, VDS2 can be VGS2 minus VTH2, correct? Or VTH,
Yes.
since VTH is there. So we know at this particular point, we have VGS2 minus VTH, right?
Yes.
Now, what we are looking at is VGS, VDS3, correct?
Yes. VGS3.
VDS3, it should be VGS3 minus VT.
VTH.
So here, if we see it as VDS3 can be written as VG3 minus VS3 minus VTH, right? So here it will be VG3 minus VS3 is already VGS2 minus VTH, correct?
Yes.
Minus VTH. So VDS3 becomes VG3 minus VGS2, and this VTH and other VTH is cancelled. So
Right.
VDS3 becomes VG3 minus VGS2, and V3 is VDS3 plus VDS2. So this is VG3 minus VGS2 plus VG2 minus VDH, correct?
Yes.
So from here, these two will be cancelled, and we are left with V3 is how much? VG3 minus VDH, correct?
Yes.
So this VG3 means at this particular potential, this potential from here to ground, what is the potential? That is what we need to know, right?
Yes.
So here, if you see, this potential is equal to this potential, correct?
Yes.
So that
Yes.
means my VG3, I can write my VG3 as VDS4, oh sorry, VDS4 plus VDS1. I can
Right.
write it this way,
Yes.
correct? So now if
Yes.
I substitute it back here, my V3 min, so this is, we are all talking about min. So V3 min turns out to be VDS4 plus VDS1 minus VTH, correct?
Right. Yes.
So this at the end gives us the value of twice of 2.97 minus 1, right?
Okay.
So this is the same thing, but I guess this red one is a better explanation to solve it because it gives you a more clear picture, correct?
Yes.
So maybe you can follow. It's a little lengthy, but rather than going for shortcuts and getting confused, better to use this particular method. So this is the best method possible. It's a little lengthy, but we have gone step by step, and you can understand each and everything clearly, right? So
Right.
I think
Yes.
you can use this method better. So it's a little lengthy, but you understood, right? How we went across.
Yes. Yes.
So basically, minimum के case में what you have to understand is minimum is with respect to the saturation limit. That is VDS minimum is VGS minus VTH. And also if you have to, like somewhere if you need VDS to start with in any calculations, you always start with the saturation limit. Because most of the times it is possible that VGS is known. At the end, you have to know the VGS to understand the operation, right? So, if anywhere you have to start with by using some value of VDS, we always go for VGS minus VTH. That is the saturation limit, and that is also the minimum VDS possible. So here also in this problem, what they were asking was this particular values. Like considering that there are minimum drops across your transistor, so what will be the V3 in your case? So from here, if you look at this very carefully, like something that you can understand is, in the previous problem, the first problem, we said the drop across my transistors was 2.97 and 2.97, right? My VDD was 12 volts. Okay. And let's say this is the point where I take my output. Okay. So here, below output, the drops across the transistor was 5.94 volts, right? But in the same circuit, when you go for minimum, like when you come to the edge of saturation and then you compute the circuit, the drop across these two transistors is actually 4.94 volts, which is 1 volt advantage. So this particular 1 volt can be used in the swing, output swing. So these are the techniques which are used to improve the output swing. Getting my point?
Yes.
So it is not just something you are doing theoretically, like it's not just for the problem solving purpose. Rather, it also gives you insights into your practical problems as well. So here you can clearly observe that you have got like an advantage of 1 volts, and 1 volt is very critical. Like if you get an advantage of 1 volt in the swing, it can increase your ICMR by some percentage. So few percent of ICMR can be improved. So bandwidth of your input signal will increase. So it's very useful, right? So getting my point. So it's not just, so these problems you might feel that you are performing some theoretical question just for the sake of problem solving, you're solving the problems. But if you look into the problems with a broader perspective, you can clearly observe that there are some practical insights also involved with these problems. Okay. So this is one of the technique that can be used in your practical scenario while designing your circuit to improve the output swing. So is this clear?
Yes. Thank you.
Okay. Yeah. So now we can move to the next problem. So this is question number 3. So question number 4. Yeah. So in this problem, again, you have a circuit. Okay. So if you observe the circuit here, you have PMOS and NMOS both. Okay. So this is more like CS stage. And here again, you can see that there is this mirroring stage as well. So definitely some kind of current transfer must be happening between one branch to another. That is very clear to us. Now here VDD is given as 10 volts. And what else is mentioned? So you have, okay, current through transistor M1. Current flowing through the drain terminal of M1 or M2 is 2 milliamperes. So this current is mentioned to be 2 milliamperes. The transistors M1, M2 are identical. So these M1, M2 are identical and 3A and 3B are identical. Because these two two PMOSs are identical, two NMOSs are identical. With that, we have to find the ratio between R1 and R2. Similarly, R3 and R4. The current ISD1 is 2 milliamperes. So ISD1 is basically the current through this transistor. Okay. Let's quickly. Yes. What I had given. So we have kW by L. Okay, kW by L for 1 is equal to kW by L for 2 is 1 milliamps. The whole square. 3W by L 3W by L 3B is 0.25 milliamperes per volt square. Remaining parameters are VTH. Mod VTH is 1.5 volts and lambda is 0.01. Okay, other than that, nothing else been mentioned. We have to find the ratio of R1 by R2 to R3 by R4. This is the formula. Okay. So we know that the current through the transistor M1, so that is I1, ID1 equal to ID3B. Similarly, ID2 is equal to ID3A since there won't be any current flowing through this particular branch or this particular mirroring connection as it has been connected to the gate terminal. So now we have ID1 that is 2 milliamperes. It is kW by L1 VSG minus VTH whole square 1 plus lambda VDS. So this is S, this is D, and this is D, this is S, D, D, S. Here also it is 10 volts. So here you have VG1 is VDD into R2 upon R1 plus R2. So if we substitute it, we'll get Vs is 10 minus Vg1 is 10 into R2 upon R1 plus R2 minus 1.5 whole square 1 plus lambda VSD. Minus VD, but it is 0.01, like 100th time, so this is very small. So to simplify the calculations, we can neglect that also. So if we neglect that, what we'll get is this milli cancel. So here you will have 2 equal to 10 times of R1 by R1 plus R2 minus 1.5 whole square. So from here we can find the value of R1 by R2, or we can go by other way around also, like it is VGS1 can be written as 2ID1 by KW by L plus VTH. So here it will be 2/1 plus VTH. So VGS1 will be 2 plus 1.5. So this is 3.5 volts. Now here you would have considered like plus minus, but we already know that if we take minus, then VGS would come out to be less than VTH, so that is not possible. That's why we have proceeded with VGS positive. So now we know that VGS1 is 3.5 volts, and we also know that VGS1 can be given by R2 upon R1 plus R2. This is 3.5. So 10 R2 is 3.5, R1 plus 3.5 R2, 6.5 R2 is 3.5 R1. So we want, what we want? R1 by R2. So R1 by R2 would be 6.5 by 3.5. So this is 13 by 7. So this is the ratio that we get. We want R1 by R2 equal to R3 by R4. Which will also come out to be equal to R3 by R4, as they are similar kind of transistors, but wait. Here what we found out was okay, so this is not VGS, right? This is VSG. Because we are talking about PMOS transistors, so it is very important that we write VSG. Why? Because the moment it is VSG, so this will change. This becomes Vs minus Vg to be 3.5. So Vs is already known to be 10, then Vg becomes 6.5 volts. Vg becomes 6.5 volt, and this particular Vg is equal to 10 times of R2 by R1 plus R2, which brings us to 6.5 R1 equal to 3.5 R2. So R1 by R2 becomes 7 by 13. Yes. This is also equal to R3 by R4, as they are matched circuits. So yeah. So because it is very important to understand that we are analyzing PMOS transistor. So like here, in case of NMOS transistor, using VG or VSG does not make much difference, because most of the time in NMOS transistor source is grounded. But in case of PMOS transistor, it is very important to write the potential properly, that is VSG, because it is connected to VDD. So it is VS like VDD minus VG, because of which the difference will come into picture. As you can clearly observe, earlier when we considered VGS and salt, it was the relation was just opposite. So this is something that we have to keep in mind. So yeah, be very careful, because yeah, this is sometimes we do make mistakes, and because of which the result will be completely opposite. So that is something that we have to keep in mind. Other than that, okay, this was question number 4. So we'll do question number 5. So in this next problem, again, it's a follow-up problem for the same circuit. So in this circuit, we have to find the precise value of DC output V out. Okay, this voltage we have to find. So So in this particular circuit, we know that M3A is identical to M3B. These two are matched transistors. So we know that VGS3 is equal to VGS3A is equal to VGS3B. So if we find VGS3A, which is also equal to VDS3A, it is root under 2 times of ID by KW by L3A plus 1.5, which is of VDH. So it becomes 2 into 2 by 0. How much was that? 0.25. 0.25 plus 1.5. So we'll get so VGS3A is equal to VDS3A is equal to 5.5 volts. Now since these two transistors are matched, bottom transistors are matched and top transistors are also matched, so VDS3A will also be matched to VDS3B, since all of the other factors are matching. So from there we can say that like VDS3B will also be 5.5, and this is the V out. So from there we can find the value of V out to be 5.5 volts. Hope this is clear. If all the transistors are matched to one another, like in two branches, if you have two branches and the transistors in branch 1 are exactly matched to the transistors in branch 2, then you can safely say that their VGS, gate voltages, are matching, as well as their drain voltages are also matching, unless there is no other load or extra component is applied. So from there we can simply write like the output to be 5.5 volts. Okay, so yeah, with this, moving on to the next problem. In this problem, we have to find the small signal voltage gain in the mid-frequency range of the amplifier. The coupling capacitor is assumed to be shorted, so this is shorted in the mid-frequency range. Okay, so from here, if we look into this, this is input, this is output, and here it is a CMOS amplifier, CS amplifier, but the only thing is here the input is given to PMOS rather than NMOS. That is the only difference. So since this is a CS amplifier, simply we know the gain turns out to be minus GM into Z out. And if we talk about Z out, so looking from this, the Z out that we will observe is coming from R01 parallel to R0 3B. So the next question is, what about the GM? Like there are two transistors, although the currents are same, the value of K is different for both the transistors, right? GM we can simply write it as twice of ID, twice of ID into kW by L. The question is, here we have same current flowing, but kW by L are different for both the transistors M1 and M3B. So which kW by L we will use? Will it be kW by L for transistor 1, M1, or will it be for the transistor M3B? Which one will be used?
M1.
Yes, we will be using kW by L for transistor M1. Why? Because GM comes from the input transistor. So input transistor gives you the value of GM. That's why we have to use the GM for the first transistor, that is the PMOS. So from here the GM will be 2 into 2 into 1. So GM is 2 millisiemens. Whereas R0, since both the lambdas are equal and currents are equal, so it will be simply 1 upon lambda I, that is 1 by 0.01 into 2 milli. So which will be 50K. With that we have our gain to be 2 millisiemens into 50 kilo. So gain is 100. This is volt by volt. Oh, wait. So this is 50K, but it should be like one parallel to another, right? So this is 50 parallel to 50. So this becomes minus 2 into 2 milli into 25K. So here it will be 50 volt by volt. Yes. Okay. So we'll have gain as 50 volt by volt. Okay. This is clear? Now coming to the next problem. In this problem, in the given circuit, CS is 3.1 picofarad, RS is 43 kilo. Okay, this is 43K. GM is given. RDS is 30 kilo ohm. CGS is 7.4 pico. with these, what is the overall transfer function? The overall transfer function is to be evaluated for this. We use the Norton's method. And what is the pole due to output impedance? Okay. So here you can compute the total transfer function and then find the pole. That is also fine. But if we have to go uh, by a shortcut method or by a simplified method, we know that whichever point we have to find the pole, at that particular terminal or at that particular position, we have to find the R effective and C effective. Correct? And we know the pole is simply 1 upon R effective into C effective. Correct? So, with this, if we see that in this particular circuit, uh, if I paste this circuit here, so from here I know I will get a small RDS which is connected between RD and ground. And this particular capacitor CGS has been connected between your input and output ports. So if I have to simplify this circuit such that I can only observe what are the components coming in the output side, how it will look like. So I will have the component due to CGS, which is one time CGS, as we have seen due to Miller effect. You will have RS, will have CS, and there will be another component, this small RDS, which will come in parallel. Correct? This is the simplified version that we will see. And in this case, your Z out turns out to be 1 upon GM parallel RS parallel small RDS. So this comes when you have a connection between input and output. So when your gate and drain are shorted, you get this factor of 1 by GM from there. So that's why this 1 by GM comes into picture. Other than that, C out will be simply CGS plus CS. And in our case, we have already found out GM. GM is given in this question, right? So 1 by GM turns out to be 680.27 ohms. Small RDS is 30 kilo ohms and RS is 43 kilo ohms. So definitely Z out will be much smaller. So Z out comes out to be, this value comes out to be 655.05 ohms. This is Z out. And C out is 3.1 plus 7.7. 7.4, so this is 10.5 picofarads. This is the C out. So the pole value is 1 upon 60, 655.05 into 10.5 picofarad. So the pole value comes out at 145.39 megaradians per second. If you want it in hertz, you can simply use a factor of 2 pi. Okay, so this is question number 7. So question number 8. So now, when we talk about the value of 0, we find the value of 0 by using the yes. So we have understood that the number of poles we find by looking at the number of AC nodes, and when we talk about number of zeros, it is about the it is found out by the number of capacitors that are there between input and output node, and their value will also be calculated by this capacitor that is between input and output. So 0 is a function of CGS, that is capacitor between input and output node. Okay, and again 0 is again given by 1 upon RC. So here, as I mentioned, when you connect your input and output together, the impedance that comes out because of this connection is 1 by Gm. So here R effective is 1 by Gm. And C, we already know C is 7.4 picofarad. So the value of 0 becomes 1 upon 1 by Gm into CGS, that is Gm by CGS, which is 680.27 by 7.4 picofarad. So the 0 comes out at 198.65 megaradians per second. So this is the value of 0. So is this clear how we find the value of 0? So both poles and zeros are given by 1 upon RC. It's just that you need to understand how to find the value of C and R, and which C and which R to be considered. In case of 0, it is the connecting capacitor between your input and output terminal that will give us that will give us the 0. Whereas in case of pole, we'll simply look into all the AC nodes, and we will calculate their corresponding R's and C's over there, and we'll get the poles. So that's how we get the poles and zeros without solving the transfer function. Or if you are not very confident in doing that, you can also go by preparing a small signal model for the given circuit. By using that small signal model, you can compute the transfer function, and from there you can equate the numerator to 0. You will get the values of zeros, and if you equate the denominators to 0, you will get the poles. Okay, so you can go by both ways, but this method is a little easier method, and also time efficient compared to solving your small signal model. But still, if the circuit is small, you can go for small signal model. It's up to you. Okay, so yeah. I'm coming back to the next problem. So, in a practical situation, a common drain is going to be used as a buffer uh, signal source with large source resistance. And consider the circuit below where the input source resistance R is 43K. GM of the device is 1.47 millisiemens and CGS is 7.4 pico. Assume that the common drain circuit is drawing an infinitely large impedance, driving an infinitely large impedance. Okay. Further, assume that RDS of the device is infinitely large. RDS is almost like much larger, so closer to infinity. When any resistance is very large, so its parallel combination will be negligible. So you can neglect it in the parallel combination. That is the only insight that you get when you say something which is in parallel and very large. So you can neglect that component in the parallel computation. Okay, so ignore the body effects. What is the magnitude of output impedance of the circuit at the frequency f equal to 3.2 gigahertz? Okay, so we have to find R. So what is the magnitude of okay, so let's say we apply a small voltage Vx over here and provide a current Ix. Okay, so if I want to find Z out, it is simply Vx upon Ix. So if I can find this, that will give me my Z out, right? Now here, if we see, this Ix is going through the transistor. This is minus of ID, correct? Because ID flows from top to bottom. If it is going the other way around, this is minus ID. Or to make things easy, let's write it like this. This is ID, this is Ix, and the current of small I will be flowing through the CGS and followed by RS, as here there won't be any current, correct? So my Ix is equal to minus ID plus I, right? Now since RDS is almost infinity, so let us consider that GDS is almost 0. So we know that small ID is GM VGS plus GD VDS. So this particular term will be eliminated. Now we have GM VGS. In this transistor, if I talk about, so this is now grounded. Okay, so at a time you analyze using one source for simplification. So this is grounded, which makes us that, okay, so this is gate, this is source. So if I have to find the value of Vg, how it will look like? So this is Vx into Rs upon Rs plus 1 upon Cgs into S, and Vs is Vx. So Id is Gm Vx Rs upon Rs plus 1 upon Cgs S plus, minus 1 minus 1. So Id becomes Gm into Vx Rs Cgs S by 1 plus Rs Cgs S minus 1 minus Rs Cgs S. So this becomes Id is minus Gm Vx by 1 plus Rs Cgs of S. So this is the value of Id. Now if I talk about S, I. So how my I will look like? I is the current that is flowing through my capacitor as well as resistor with Vx. So Vx upon R plus 1 upon Cgs S will give me my current I. This is also known to us. So Ix is minus of Id plus I. So this is minus of minus GmVx by 1 plus Rs Cgs into S plus Vx Cgs is 1 plus Rs Cgs of S. So Ix becomes Vx Gm plus Cgs S by 1 plus Rs Cgs of S. So Vx by Ix, that is Z out, will become 1 plus Rs Cgs of S by Gm plus Cgs of S. So this is the value of the expression Z out, right? Now here you know the value of Gm, Cgs, Rs, all, and you know S equal to J omega. That is S equal to J into 2 pi into F. So this is how much was it? 3.2 giga, right? So S equal to J into 2 pi into 3.2 into 10 to the power 9. So you can substitute this in this value, like this expression, and then you would need to find the magnitude of it because it is an because it will come in a, what we call it, it will come in J term, right? So you have to get the real part of it. So for that you have to compute the value of this magnitude of this expression by substituting the value of J. Okay, then you can get the value of Z out. Now, moving on to the next problem. So this was problem number 9. So problem number 10. Question number 10. So in question number 10, what is the magnitude of the output impedance of the circuit at the frequency of 28 kilohertz? So again, it's the same thing, it's just that frequency has been changed. So you have seen that Z out is 1 plus RSCGS S by Gn plus CGSS CGS of S. So if I have to find the magnitude, would be root under 1 plus RS CGS omega 1 square plus R square C square omega square by Gm square plus CGS square omega square. So by this we can find the magnitude of Z out. So if I have to give the values, so Z out magnitude at 3.2 gigahertz is 42.998 kilo ohms. Similarly, the Z out at 28 kilohertz is 681.337 ohms. So here one more thing that we can clearly observe is that Z out is directly proportional to the frequency, right? So as the frequency is increasing, the Z out value is also increasing. So coming back to the final problem for today. So here it is given your observation of output impedance of common drain amplifier circuit when the input voltage source has a large impedance. What can you infer about the quality of this output impedance? Like output impedance, is it resistive in nature? Is it inductive in nature? Is it capacitive in nature? Or is the output impedance low? So first of all, when we say a resistive nature basically means Z out should not be a function of frequency. Okay. Inductive nature means more or less it should be like Z out should be a function of frequency and Z out should be directly proportional to the frequency. If it is directly proportional to the frequency, then it is inductive in nature. As we know, Z out is omega L in case of inductance. Now, if it is capacitive in nature, then again Z out would be a function of frequency. However, Z out will be inversely proportional to frequency. Why? Because Z out is 1 by omega c, right? In case of capacitance. So because of that, it will become inversely proportional to frequency. So till now we have observed, like in the two above problems, that as the frequency was increasing, the Z out was also increasing. So that means Z out is directly proportional to frequency. If it is directly proportional to frequency, that means it is showing an inductive behavior. Is this clear?
Yes.
Okay. So that's all for today's problems. This was the final problem for today. Any doubts? So were the problems which were solved today were clear to everyone? Okay. So next time we will look into the stability concern, like how we analyze stability and everything. And yeah, other than that, is the concept of cascade and cascode clear to everyone? The advantages, disadvantages that we discussed.
Yes.
Okay. So if you have any doubts, you can unmute and ask. Else we can end the session today here. And we'll meet next week with new set of problems and concepts. That's all for today.
Thank you.
Thank you. Any doubts, like Jyoti, Vinod, Bhuvan? Do you people have any doubts? Okay. What about Jyoti and yeah, Jyoti? Hello? Jyoti, were you saying something?
No, ma'am. No.
Oh, okay, okay. So if you don't have any doubts, you can leave the session.
Oh.
How about Bhuvan?
Mm.
Any doubts, Bhuvan?
No, ma'am.
Okay, so if you people don't have any doubts, maybe we can end this session today over here. And we'll meet next week with new set of concepts and problems. So that's all for today. Thank you for joining. Bye. Have a wonderful evening ahead.